Good afternoon, students. We are back once again with another topic of physics, which is electrostatics. Okay, now by the word electrostatics, what do we understand? Electro, definitely it deals with electricity, but with statics we mean when the charges, they are not moving, they are not moving, they are static, or they are when the charges are static, they are not moving. What are the properties associated with the charges? Now you know that there are two kinds of charges. One is positive, one is negative. These things you know from your preliminary classes, that like charges, so if plus and plus charge, they will repel, or minus and minus charge, they will repel, but the opposite charges, they will attract. So when they're attracting with some force. So we will study with what force they are attracting, and what is the electric field, electric potential, all this notations, all these terms we will study in this whole chapter. Okay, first to start with, like, you know what is the elementary form of charge? The elementary charges is a charge of one electron, because we don't have particles which are smaller than electrons which have charges. So a charge which is the smallest charge, it is a charge of one electron, and that you know is 1.6 into 10 to the power minus 19 coulomb. Minus is for the negative charge. So the charge of one proton is nothing but plus 1.6 10 to the power minus 19 coulomb. Now whatever electric charges we have in nature, they are an integral multiple of E. That is, all the charges we have in nature should be n into E, where n belongs to integer. So n cannot be a fraction, like n cannot be 1.5, n cannot be 2 by 3, or like this. So we cannot have charge like 2 by 3 electrons. No, whatever charges we have, we get like this. Now you know, for 1 coulomb of charge, so how many electrons will be there is nothing. For 1 coulomb of charge, the number of electrons will be 1 by 1.6 into 10 to the minus 19. If you calculate, it will be about 6.25 in 10 to the power 18 electrons. Okay, now what we are talking about, the charges, the forces between these charges. Now the charges, whatever charges we will talk about, are integral multiple. So integral multiple means it has another name, that is called the charges are quantized, right? Okay, now for the force, for the forces between the charges, forces between two charge Q1 and Q2 is nothing but force equals to 1 by 4 pi epsilon 0 Q1 Q2 by R square. That is, the force between two charge is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. And the constant which is getting multiplied is 1 by 4 pi epsilon 0, where epsilon 0 is called the permittivity of free space. Now this 1 by 4 pi epsilon 0, this constant has a value 10 to the power 9 into 10 to the power 11. You can see what would be the unit of this. See, force is Newton, so Newton meter square per coulomb square. Now how do they came, we will study later. Now epsilon 0 is a property of the free space. So in free space, the constant with which the charge multiplies is this. Okay, this will be 10 to the power minus 11 because this force is very, very small. 1 coulomb. I'll just check. I'll just check with this. Okay. After that, see. Now, suppose there is a force of repulsion. There is a force of repulsion between these two charges when the medium is free space. Now, instead of free space, some dielectric constant is inserted between this. Now, what do we mean by the word dielectric constant? It is they behave as insulators, but what happens in place of charges, influence of charges, they do behave as charge dipoles, and it modifies the force between these two charges. Now what happens in place of dielectric constant, the force that is generated between the two charges, it gets reduced by a factor of k, where k is called the dielectric constant of the medium. This medium has a dielectric constant of k, and so what happens, the force, the modified value of this force, it becomes 4 pi epsilon 0 k q1 q2 by r square. Got it? Where k is called the dielectric constant of the medium. Now, we will study today electrostatic force, then electrostatic field, potential energy, and potential. Mainly these four things. Now we have discussed about electrostatic force. Now what we have? Electrostatic field. Now from the concept of gravitation, you know, any field is nothing but that is the region in which the charge is acting. That is, suppose we have a charge plus q, then the region through which the charge is acting, this is called the region of the charge, and this area is called the electrostatic field region. Electrostatic field can be defined as the force per unit charge. Now see, suppose there is a charge q and there is another test charge q0. What is the force of repulsion? Force of repulsion is 1 by 4 pi epsilon 0 q0 by r square. Now, if I divide by q0, then electrostatic field will be E equals to F by q0 will be 1 by 4 pi epsilon 0 q by r square. Now, as in force, electrostatic field is also a vector quantity. All these things are vector quantity. So if suppose there are a lot of charges within the system, all the charges will have a force vector associated with it. Suppose this charge, right, there are so many charges, the force will be the net force will be the summation of all the individual forces. Same thing can be told in case of net electrostatic field. So E will be summation of all electrostatic field. Now we have studied electrostatic field for a point charge. That what we have studied, 1 by 4 pi epsilon 0 q by r square. Now we can find electrostatic field for a ring of charge. Suppose this is a ring of charge, right, which is Q, which is the ring is of radius r, and we want to find the electrostatic field at a distance of x from the center of the ring. Now what will be the electrostatic field? If it is plus, the electrostatic field will be E, right? This E, this can be given as 1 by 4 pi epsilon 0 q x by x square plus r square root 3 by 2. There is a question whether this video will help you in the AIMS exam. Yes, this is nothing but we are doing it for joint entrance mains, and these are the basic knowledge about electrostatic. We will be also discussing on few questions which are quite similar to joint entrance mains and also for your AIMS exam. You just follow the video. Okay, now electrostatic field, see this formula you can derive it. You don't have to derive it right now, because what we need to do, we need to apply it. I'm explaining it once more. There is a ring which is having a charge Q with it. Now we have to find out what is the value of the electrostatic field E at a distance of x from the center of the ring, which is having a radius r. That is given by 1 by 4 pi epsilon 0 qx by x square plus r square root 3 by 2. See, very interestingly, if this x distance is much greater than r, then what happens? This term becomes, E becomes 1 by 4 pi epsilon 0 qx. X square is much greater than r square, so r square you can ignore. It becomes x square by 3 by 2, which becomes, this becomes x cube. X cube in the denominator means x and x cube, so it finally cancels. It will become 1 by 4 pi epsilon 0 q by x square. So when x is much greater than r, this ring will behave as a point charge. Whereas secondly, if we take 0, that is, we are considering the electric field at center. What will happen? If x becomes 0, if you put the value of x at 0, E becomes 0. So at the center, the electric field is 0. That you can also try to think with help of symmetry, because all these point charges, all the positive charges will have what? The electric field will be directed towards the center, right? And they will cancel at the center. So electric field at the center is 0. Okay, now we are coming to electric field due to a line charge. Due to a line charge. A line charge means, suppose we take any conductor. Suppose it is, this is having charge Q. The total length of this charge distribution, say it is 2a, right? Now we are trying to find out what is the electric field at a distance of x. Now see, you will see, similarly for the line, the electric field, there is a formula which is given by Q by 4 pi epsilon 0, or I can write it like this. Plus, see, this distance is a, it is root over x squared plus a squared. Now what does this mean? At when this line distribution is q for within a distance of 2a, from the center it is a and this is minus a, and the distance here is x, so electric field will be 1 by 4 pi epsilon 0 into q by x root over x squared plus a squared. Okay, now what happens? See, here also we can have two condition. If x is much greater than a, so what you can predict, if x is also much greater than a, so this line also will behave as a point charge. See, if x, so x square is much greater than a square, so this part will vanish, so root over x square becomes x, so x into x is x square, so E becomes similar to point charge, right? And if x is much less than a, that is x which is very close to this, now what will happen? Now when x is very close to the line where a is much long, that is a is a huge line of charge, then what will happen? See, here we can do some simple mathematics. See, E I can write from this equation, we can write E equals to Q, we will keep x, say we are bringing in a outside, so it becomes what? A, and this will become x by a whole square plus 1. When x is much less than a, x by a is very small, so this will be more smaller, so this will be ignored with 1. This is we can just ignore this term, so E will be 1 by 4 pi epsilon 0 q by xa, because this is we have ignored. Now see, we can write it in a different way. See, if q is a charge distributed over a length of 2a, we can define another quantity called lambda. Lambda is called the linear charge density. So what is this lambda? Lambda is called the linear charge density. If we see, this is the charge distributed over a distance of 2a. The linear charge density is nothing but q by 2a. So lambda can be written as q by 2a. And we can write this in terms of lambda. What we can write? See, 1 by 2 pi epsilon 0, right, q by 2a into x into 1 by x. So this becomes lambda. So we can write it is 1 by 2 pi epsilon 0 lambda by x. This is nothing but electric field for a line charge when a is much greater than x. Okay. Now let us try to draw some electric field diagram for some simple charge distribution. Now you know minus and plus, so the force between minus and plus will be, that is, it is attractive. An electric field always originates from plus and ends in minus radially, right? So all will be like this. This is plus, this is minus, and here electric field will be coming towards it. See, try to understand. For minus q, it is coming towards the q, and for plus, now what will happen if we take electric the charges for two similar this will try to go radially, but what will happen because of this, the forces will be let's just take this. Sorry for the interruption, for the technical error. Okay, now see, this is plus Q and this is plus Q. So the electric field, it will be radial, it should be radial, but because of the presence of this positive charge, the electric field, you know, they will curl because of this repulsion. Got it? So this is for when there are opposite charges, this is for similar charges. And for plus Q, always remember electric field originates from this, and for minus Q, electric field comes towards this. Got it? Now, so we are done with electrostatic force of attraction and repulsion, electric field. Now we are coming to electric potential energy. Now potential energy, you must be knowing from your previous knowledge that electrostatic force is a conservative force. So potential energy is nothing but the negative of the work done. Okay, so what is the work done? The work done, we can find out, that is work done, you know, is nothing but force into displacement, right? So for a small work done, we can write F into dr. Now the total work is nothing but integration of F into dr. Now say there is a charge Q, right? You are bringing another plus Q charge very near to it, right? You are bringing another plus Q charge very near to it. This is a technical problem happening. Cut this. Stop streaming. The coils are getting. Sorry for the interruption. It's a technical problem. Where I was? Okay, the electric potential energy. So see, there is a positive charge Q. You are bringing another positive charge from infinity to a particular point, right? Say this charge is Q1, this charge is Q2. Now what will happen? Try to understand physically. There is a positive charge, another positive charge you are bringing in, so it is repelling. So you are doing some work in order to bring it nearer to its vicinity. This work is getting stored as a potential energy of the system. Now if we try to calculate the force between these two charges, r square, so the work done will be integration of, that is 1 by 4 pi epsilon 0 q1 q2 by r square Just tell I'm coming within. Right? We'll be doing numericals within five minutes. I'll be just going through it very fast. Right? So from A to B, or from infinity to a particular point, and if you do it, you will see the work done, the potential energy is nothing but minus of work done, which is nothing but 1 by r. Okay. Now for a Q1, Q2, for a system of charges, right, you will be nothing but, now potential energy is a scalar, is by r. Now this is potential energy. Now what is potential? Potential is nothing but potential energy per unit positive charge, that is U by Q0. So you can have for 1 point charge 1 by 4 pi epsilon 0 Q by R. Right? You can deduce for a ring V becomes 1 by 4 pi epsilon 0 Q by R squared by X squared. Right? Where R is nothing but the radius and X is nothing but the distance from the center. Okay. Now electric field, you know about equipotential surface. You know, right? Equipotential surfaces are those surfaces which has same potentials. So what will happen if they are in having same potential? The work done within equipotential surface will be 0. So no work is done within equipotential surface. There is no difference in potential within the equipotential surface. Equipotential surfaces, they don't intersect with each other, and the field, electric field, is always perpendicular to the electropotential surface. For to know this, you need to understand another thing. Electric field is nothing but minus dV dr. That is, it is the gradient of potential, or potential can be written as minus E dr. We will use all these things in our problems. Okay, now electric dipole. So we are done with force, field, potential energy and potential. The last part is electric dipole. Electric dipole, you know, plus Q minus Q separated by a distance of 2a. The dipole moment is always directed from negative to positive, is Q into 2a, right? And you know the formula, that formula you can find out. Just know this one. The torque to rotate one dipole is nothing but PE sine theta. What does this mean? That is, there is a dipole within an electric field. Say this is minus Q, this is plus Q. So the dipole moment is directed along this direction, right? And the electric field, this is dipole moment. Electric field is in this direction. The angle between them is theta. So the torque that this dipole is, experiencing is PE sine theta. That is P vector cross E vector. Okay. Other things you can see from your book. Let us try to solve few problems. Okay. Interesting. We have the first problem is on electric dipole only. See, this is a very interesting problem. an electric dipole has a fixed dipole moment P, which makes an angle theta with respect to the x-axis. So the electric dipole P is making an angle theta with the x-axis, right? And the dipole moment is P. When subjected to an electric field E1, which is equals to EI, I is the unit vector, it's I cap E1 is then directed towards the x-axis. You can say E1 itself is directed towards the x-axis. It experiences a torque T1 equal to tau K. Now see, the torque T1 is nothing but the cross product between P and E1. Now see, P is at an angle of theta with the x-axis. E1 is EI. It means what? That the E1 is directed towards the x-axis. So the angle between T1 and angle between P and E1 is theta. So the torque T1 will be nothing but P E1 sin theta. Now when subjected to another electric field E2 equal to root 3 E1J, here lies the crux. E2 equal to root 3 E1J. So what does this mean? The dipole, now this dipole is directed along the y-axis. Sorry, this electric field E2 is directed towards the y-axis. Dipole is in this direction, theta. So what is the angle between the dipole and the electric field? It is nothing but this one. This is 90 minus theta. So the torque T2 is nothing but PE2 sine 90 minus theta. That is P root 3 E1. This is cos theta. Understand? Now they have given T2 equal to minus T1. If we just ignore, we can just ignore this minus for the time being. We can say the magnitude of these two torques are equal. So T2 equal to T1. So we can say magnitude of they are equal. So we can write P root 3 E1 cos of theta equals to P E1 sine of theta. P cancels out, right? E1 cancels out. Now if cos theta goes this direction, so root 3 becomes tan theta. So theta becomes 60 degree. So we have to find the angle theta is 60 degree. It came in joint entrance 2017. Understand? Okay. We'll try to see another problem. Assume that an electric field E equals to 30x square I that exists in space. Then the potential difference VA minus V0, where V0 is the potential at the origin and VA the potential at x equal to 2 meter. This is a very straightforward problem. Why? Because we know electric field equals to minus dV dx. So V is definitely minus E dx. X is ranging from 0, origin means 0, and x equal to 2. So we can write minus, in place of E we should write 30x squared, and x is from 0 to 2 dx. This is 30x cube. Minus should always be there. That is 10x's, that is minus 10x cube. So by putting 2, you will get it is minus 80 joule is the answer. Right? Minus 80 joule is the answer. Clear? So for solving these kind of problems, you don't need to know the formula. I mean the derivation of the formula always. You definitely need to know this. But solving problems of your competitive exam, you just need to know the basic concept and the formula, and you have to apply them. See how we do this problem. This is a very interesting problem. Two identical balls, each having density rho. These are the two balls. They are having a density rho. Right. The density is rho. Are suspended from a common point by two insulating strings of equal length. These are the strings. Both the balls have equal mass and charge. Right? So the mass and charge is the same. So what will happen? So the charge we can assume to be Q and mass, suppose it is M. In equilibrium, each string makes an angle theta with the vertical. So what will happen? As they are having the same charge, so they will repel one another. They are repelling. The force of repulsion is in the horizontal direction, but the weight is in the vertical direction. So finally what will happen? The string will be separated. So suppose these are the two strings. They are the balls. If they are repelled, they will finally stand like this in the equilibrium. Right? This angle is theta. Okay. Now both the balls, now is very interesting. Both the balls are immersed in a liquid. Now see, when the whole system, the whole system is in free space. Vacuum, air, free space, all be considered to be same. There the dielectric constant or the force, the electrostatic force of constant is 1 by 4 pi epsilon 0. Now both the balls are immersed in a liquid. When they are immersed in a liquid, then the dielectric constant K comes into account. So if the liquid has a dielectric constant, say K, we have to find that one. As a result, the angle theta does not change, but the angle is not changing. The density of the liquid is rho. Find the dielectric constant of the liquid. Now say what is happening. First, initially this is the system. Now when it is immersed in a liquid, now what is happening? Theta is not changing. Why? Because see the force itself, the force of repulsion, say it is Fe dash, because of this dielectric constant, it is reduced by this constant K, so Fe by K, right? And also force is reduced. Also see what happened to the weight. The weight of the body is also reduced because the liquid is having some upthrust. And definitely the tension T dash will also modify. Now let us try to solve how we can get this dielectric constant K. See, let us first analyze this one. See, for one single charge, we can use the Clannish Theorem, right? See, there are three forces acting. This is theta. It means this angle is also theta. Now W by this whole angle is sine 90 plus theta. Clannish theorem says what? When three forces are acting simultaneously at the same point, if F1, F2, F3 and the opposite angles are theta 1, theta 2 and theta 3, then F1 by sine theta 1 will be equal to F2 by sine theta 2 will be equal to F3 by sine theta 3. Right. So as they are in equilibrium, so W by this whole angle sine 90 plus theta must be equals to Fe, that is the electrostatic force of repulsion here, by this angle. This angle is what? 180 minus theta, that is sine, so which can be written as W by this will be cos of theta. This will be Fe sine of theta. Got it? Now what is happening? The same thing when we are inserting it within the liquid. Then what is happening? This force is getting modified, is getting reduced by the dielectric constant K, and also the weight W dash. But this equation will remain the same. So if we say this is 1, and we can say this is W dash, because this angle is also theta, by cos theta will be equals to Fe dash by sine theta. Now from this two equation we can write this divided by this, so W by W dash equals to Fe by Fe dash. Now Fe dash is nothing but Fe dash Fe by K, because it is a liquid. It has the force of repulsion has reduced by the dielectric factor K, so this will become K, right? And so K will become W by W dash. W is the weight of the ball. Weight of the ball is nothing but the volume of the ball into density of the ball by the gravity. And what is now this weight is what? This is nothing but the actual weight minus the upthrust. This is the apparent weight. This is W dash. So it is nothing but W minus upthrust. What is that? V rho G. W is again V rho G. Upthrust is the whole body is immersed, so definitely it is V into the density. The density of liquid is rho. Rho, this is sigma, this is G. Now see, V and G all cancels out. It becomes rho by rho minus sigma. So finally, the dielectric constant we can get in terms of ratio is nothing but the density of the solid minus the difference of density of the liquid. So similar kind of problem will come in your competitive examination. Just know the formula and know how to apply them. Right? So today what we have studied about electrostatics part 1, about the electrostatic force of attraction and repulsion, electric field, the electrostatic potential energy, electric potential and electric dipole. We'll continue it this chapter tomorrow also. Thank you.